We can now start the Symmetric Cryptanalysis 2 session. We have 4 talks in this session. The first one will be on Zoom, and the last one will be a pre-recorded video, and the 2 other speakers should be here, hopefully. So the first talk is about revisiting differential linear attacks via a boomerang perspective with application to AES, ASCON, Clefia, Skinny, Present, Knot, Twine, Wrap, L-Block, CMEC, and Serpent, and Hossein will give the talk.
Thanks for introduction. Everybody can hear me? Okay, yeah, thanks, Gaëtan, for the introduction. I'm Hossein Hadipur from Graz University of Technology, and today I'm very happy to share our discoveries and results regarding differential linear attacks. We looked at differential linear attack via a boomerang perspective because when I started this work, I had a great background in boomerang analysis, and I realized that a lot of tools and developments in boomerang analysis can be reused in differential linear attacks. So with this idea, I reached out to my co-authors, Patrick Derbez and Maria Ayşosede, and together with their help, we could actually answer 2 important questions in this context. The first question was how to analytically estimate the correlation of DL distinguishers. By DL in this talk, I mean differential linear distinguishers. And the second question is how to efficiently search for DL distinguishers. To answer the first question, we generalized the DLCT table from Eurocrypt 2019 paper, and we answered one of the open problems in this paper. The open problem was how to estimate the correlation when the middle part of the DL distinguisher includes multiple S-box layers, because DLCT was originally proposed for handling 1 S-box layer. And to answer the second question, we developed an automatic tool to search for DL distinguishers, which is applicable to a wide range of symmetric key primitives from AES to ASCON. So let's start by reviewing a few basics about differential linear attacks. The core idea of differential linear attack is essentially combining a short differential distinguisher with a short linear distinguisher to build a more powerful and longer distinguisher for block cipher. Imagine we have a block cipher E such that we can divide it into 2 parts, namely EU and EL in this shape, such that there is a good differential trail for the upper part with probability P, and there is a good linear distinguisher for EL with correlation Q. Then we can build a distinguisher like this. We can random, and then we can apply difference delta I to P1 to generate P2. Then we encrypt P1 and P2 and generate 2 ciphertexts, namely C1 and C2. And then we look at the difference between C1 and C2, namely delta C, and we compute this bit, which is the dot product of lambda O and delta C. Lambda O is the output mask, and it is a fixed vector. So we compute this dot product, which is essentially 1 bit, and it's a binary random variable. If this binary random variable is biased towards 0 or 1, we can distinguish the block cipher from a random permutation. And the correlation of this binary random variable, namely lambda O dot delta C, is approximately equal to PQ squared under these 2 assumptions. But these 2 assumptions, unfortunately, are not held in practice. And that's why these days we use a more advanced framework, which is called sandwich framework, to build DL distinguishers. In this setting, we divide the block cipher into 3 parts, where the middle part, this green part, EM here, is in charge of handling the dependency between EU and EL. And to compute the correlation, we consider the clustering effect, the fact that delta X, the difference here, and lambda Y here are like arbitrary values. They can take any possible values. We consider this clustering effect, and we compute the correlation by this sum of product. And in this sum of product, if you look at this product, it's a multiplication of 3 terms. The first term comes from the probability of this differential trail, delta I to delta X. And the second term, R, represents the correlation of a small DL distinguisher in the middle. And the last term, which is a C squared, is actually the S squared correlation of the linear approximation for EL. But we can simplify this formula further. If you choose if you decompose the cipher appropriately, especially if you set the length of EM long enough, and if you choose delta M and lambda M appropriately, then you can estimate the sum of product by only one of its dominant terms, which is PRQ squared. And in this formula, P is the probability of a differential with input difference delta I and output difference delta M. Note that delta M is fixed, and lambda M is also fixed. To compute P and Q, we already have enough knowledge. We can use DDT framework, for example, to compute P, and we can also use LAT framework for computing Q. But we didn't know how to compute R until Eurocrypt 2019, where the DLCT was proposed. This shape on the left represents the middle part of DL distinguisher when it is composed of only one sparse layer. So we have the input difference delta I and the output mask lambda O. What DLCT does is essentially pre-computing the correlation for all of the possible input differences and all of the possible output masks, and it stores all of them. So whenever we fix delta I and lambda O, we can refer to DLCT and read the correlation, right? It makes our life easy. But when the middle part includes only one sparse layer, the question is, what happens if the middle part includes multiple sparse layers? And it was actually one of the open questions in this Eurocrypt 2019 papers. And we replied this question. We provided an analytical framework to estimate the correlation of DL distinguishers when the middle part includes multiple sparse layers. But before I explain our method for you, I want to give you a motivating example. This shape represents the best differential trail for 4 rounds of AES. And these highlighted cells are representing the active cells in the best differential trail. As you can see, there are 25 active sparxes in this best differential trail. This is also similar for linear trail. If you count them, there are 25 active sparxes. And given the fact that the differential uniformity of AES sparks is 4, the probability of best differential trail is always lower than 2 to the power of minus 150. And it means essentially there is no differential, there is no basic differential distinguisher for 4 rounds of AES. But interestingly, we discovered a differential linear distinguisher for 4 rounds with complexity of 2 to the power of 63. If you compare it with the complexity of basic differential distinguisher or basic linear distinguisher, which is 2 to the power of 150, you can see the great advantage, right? It represents the power of a combined distinguisher compared to a basic distinguisher. Here we are comparing differential linear distinguisher with differential or with pure linear distinguisher. You can see the great advantage, right? But besides this great advantage, it also raises a question here. Because in this distinguisher, as you can see, the length of the middle part is 3. And now we have 3 sparse layers. And the question is how to analytically estimate the correlation in these cases, right? So to answer this question, we generalize the DLCT framework. And it comes from the methods and ideas from boomerang analysis. What we did was that we first looked at the middle part when it includes only one sparse layers, but besides delta I and lambda O, which are considered in DLCT, we also consider several other cases. For example, if you look at the involved parameters in this case, you see that we have input difference for the sparks, which is delta I, and we also have output difference delta O. We have input mask lambda I and output mask lambda O. But in DLCT, only delta I and lambda O are considered. What was missing, for example, in DLCT what were missing were actually delta O and lambda I. So we try to generalize this DLCT table for several cases. We first define upper DLCT by considering delta O. When delta I, delta O, and lambda O are specified and are fixed, we can refer to this table and we can realize what's the correlation. We do the same by considering the linear trail. If you consider lambda I, delta I, and lambda O, you can refer to LDLCT, which is called lower DLCT. We also defined a very generic table, which is called extended DLCT. And in this table, we actually consider all of the involved parameters. You can even define more complex tables like double differential linear connectivity table, which essentially handles 2 consecutive sparse layers, where there is a key addition and linear layers in between. And now we have these 5 tables. And I claim that using these 5 tables, we can essentially formulate the correlation for any number of rounds. And yeah, as we did, for example, in boomerang analysis, right? These are just alternative tables alternative tables in BCT framework. For example, let me give you an example. This shape represents a 3-round distinguisher, DL distinguisher for AES. At the top row, you see the differential trail, and at the bottom row, you see the linear trail. We first look at the interaction between these 2 trails, and we only care about the common active sparks between these 2. We don't care about the sparks which are active in as much one of these 2 trails. We can bypass them for free, okay? And for each sparks, each common active sparks between the 2 trails, we look at its activeness pattern at the input and output to see which differences or linear masks are specified. And then we refer to the corresponding table. We replace this, for example, in the first round, this sparks is active in differential and linear trail. So this is a common active sparks. For this sparks, if you look at the shape, you will see that the input difference, the output difference, and the output mask are specified. So it means we should replace this sparks with UDLCT term in the formula. And for this, for the second round, if you look at the common active sparks, which is this one at the top, you can see all of the input-output differences and input-output mask are specified. So we should replace these sparks with EDLCT. This way we can, actually there is a guideline using which you can understand which term should be used, for example, in the formula for each common active sparks. And then by the end, you derive a sum of product, and it estimates the correlation of distinguisher. If you fix the input difference to 1 and the output mask to 9 here in this example, you can see the correlation is 2 to the power of minus 7.94 based on this formula. But if you perform experiment, you can see that the experimental value closely aligns with this estimation, and it represents the quality of our formulation. Let me show you another example. This shape represents a 9-round differential linear distinguisher for TOIN, which is a generalized Feistel cipher. And the red and blue are representing the differential and linear trail and the overlap between them. As you can see, only 6 sparks are commonly active between these 2. So only the 6 sparks come into effect. And then we can follow the guideline and create this formula. And as you can see, this table represents, compares the analytical estimation with the experimental result. As you can see, the formula is estimating the correlation very accurately. I don't want to go through the detail. I just want to show you that the formula is accurate enough. So now we know how to analytically estimate the correlation. But the question now is how to find good differential linear distinguishers, right? To give you an intuition about how a good differential linear distinguisher is, I want to draw your attention to differential linear switches. For that, let's take a closer look at the DLCT of 1 sparks. Doesn't matter. I just chose it at random. This is a 4-bit sparks, and this table represents the DLCT of this sparks. First of all, if you look at the first row and first column, you can see all of the entries are maximal. And it's because of the fact that if for a certain sparks, the input difference, namely delta I, or the output mask, lambda O, is 0, then you can bypass these sparks for free. But interestingly, there are also some non-trivial maximal entries in the middle of this table. We call them bitwise switches, and we figured out we can capture most of these bitwise switches by the concept of deterministic trails. In this slide, the red propagations represent deterministic differential transitions, and the blue transitions represent deterministic linear transition, but in backward direction. If you look at this example, you can see that the maximal entries in the middle of table appears when there is essentially no overlap between the difference and linear mask. It means when the overlap is between, I mean, in terms of activeness, where the overlap between difference and linear mask is 0, the correlation is 1. You can bypass this box for free. And it is the core idea of our search, actually. We try to minimize the overlap between differential and linear trail in the through the middle part. When we are searching for a distinguisher, we try to minimize the overlap between the differential trail and linear trail. And with that in mind, let me explain how our automatic tool works. Assume that we want to create an optimization problem to find a differential linear distinguisher with a maximum correlation. We want to maximize the correlation, right? Given block cipher E, we first divide it into 3 parts, namely EU, EM, and EL. Then we model the propagation of differential trail through EU and EM. But while we follow the normal propagation rule for EU, we switch to deterministic propagation rules for EM. And we do the same, but for linear trails and in backward direction. We model the propagation of linear trails through EL and EM in backward direction. Again, while we follow the normal propagation rules for EL, we switch to deterministic propagation rules for EM. Why we switch to deterministic propagation rules for the middle part? Because we want to capture cell-wise switches and bitwise switches. And assume that these variables in our optimization problem are representing the activeness of these certain positions like S boxes or beats in differential trail or linear trail. Assume that they are representing the activeness and there are binary variables 0 or 1. Then we set the objective function to this function. And as you can see, the idea behind this objective function is essentially minimizing the overlap between the differential and linear trail in the middle part because of this term. If you look at this term is equal to 1 if and only if the corresponding position is active in both differential and linear trail, right? And the first and last term are just simple terms to minimize the weight of differential and linear trails, right? And this is the overall view of our automatic tool. And this slide represents the black box view of the tool. Essentially, when you are looking for a differential linear distinguisher using our tool, you should specify the lengths of different parts, and then you run the tool, and what you get is something like this, an almost complete specification of the distinguisher. For example, this is one of the results that we derived for the first time for AES. It is a differential linear distinguisher for 5 rounds of AES. And the configuration of our search in this case is 1, 3, 1. It means we decompose 5 rounds to 1 plus 3 plus 1. And we consider the middle 3 rounds as the as EM, which is in charge of handling the dependency. And we compute the correlation of the middle part by our theoretical framework. This is, for example, one example how the tool works and how the output looks like. And this is another example for OSCON. For example, the left shape represents the 4-round deterministic differential linear distinguisher that we derived for OSCON. If you look at this shape, you can see there is essentially no overlap between differential and linear trails. And because of this fact, the correlation should be 1. So we come to the end of this talk, where I'm going to point to some of the future works. One of the interesting future works could be extending our tool to ARX designs. Another interesting future work could be extending our tool to a unified model for finding complete DL attack. Before I finish, I would just like to mention that I have published the source code of this tool in GitHub under this link. So thanks for attention. If you have any questions, I would be happy to answer. I cannot hear you. Yeah, I can hear you now.
Are there questions in the room? Okay, I have a, well, you mentioned it as future work already, but could you comment on how you expect this to work in terms of key recovery? Because you mostly explain what happens with distinguisher, and of course, the goal of a distinguisher usually is to be used in a key recovery. So do you expect improvements over the state of the art, or is it more complicated?
Yeah, I believe once we can unify this two, like key recovery phase and distinguisher phase, of course, we expect to be able to improve the previous results, because in the previous attacks we searched for distinguisher and key recovery separately, so they are not optimized for each other, right? And so I believe if we can unify it, of course, like what happened in the context of boomerang analysis, once we could unify the tools for searching different distinguisher and key recovery, we could improve, for example, a lot of attacks on AES and skinny. I think this could be like initiative or like an initial work. I think we can improve the key recovery if we can unify, and I think we can follow the same ideas again. We try to show that, okay, a lot of tools from boomerang analysis can be translated to differential linear, and why not doing it for key recovery? I mean the core ideas can be reused. Yeah.
Thank you.
Thanks for your question. Yeah, before I finish, I would just like to say one comment. Actually, I couldn't add in person because of visa issues. I applied for visa 3 months ago, and unfortunately, my visa application was left in limbo, and it means they neither denied nor accepted, and it was completely uncertain and very frustrating. I hope maybe ISR community wants to reconsider where to hold crypto. Maybe rotating it between North and South America could be a good idea, or improve the accessibility or geographical diversity. But I think, yeah, it's okay. Yeah. Thank you so much for your time. Yeah.
Yeah, it's probably a topic for the membership meeting, but that was yesterday. Maybe for next time.
Yeah. Thank you. I hope you had a great time in crypto. And yeah, thanks.
So we'll move to the next talk. Is the speaker here for the next talk? Zhongfeng Niu? No.
What is this? Sure. Okay. So this is laser. Okay.
And the slide events.
This is okay.
Okay, so the next talk is titled Speeding Up Preimage and Key Recovery Attacks with Highly Biased Differential Linear Approximation. It's a joint work by Zhongfeng Niu, Kai Hu, Siwei Sun, Ziyu Song, and Meiqing Wang. I'm sorry if I'm mispronouncing some of those. And Zhongfeng will give a talk.
Thanks for the introduction of the crypto. And today I will do the presentation about how to use the highly based differential linear approximation to speed up the preimage and key recovery attack. It's all. It's not working. Yeah. It's not working. No, yeah, it's not working.
It's this one, I think.
Sorry. This is the joint work with Kai Hu, Siwei Sun, Zhi Zhang, and Meiqing Wang. Firstly, let me to introduce the background and motivation. For the searching for the preimage and the secret keys are the central topics in the symmetric cryptanalysis. But however, for the permutation-based primitives, the techniques are very limited. For example, for the sponge-based hash functions, such as SHA-3 and SN-XOF, because there's the algebraic degree of their S-box is only 2. So we can use the linearization techniques to do the preimage attack. However, for the H or XOH, which is the nearest LWC finalist sparkle, the sparkles the lightweight function. There is not known cryptanalysis about this hash function. If the nonlinear operation of this some hash function is very complex, we have no way to analysis on it. And second, for the sponge-based AADs such as SCON and SHRAM, for SCON, because the algebraic degree of their S box is only 2, so we can use the Q attack to do the key recovery attack. So there is many known cryptanalysis on SCON, but for the SHRAM, there is only the designers gave some the attack, but their attack is beyond the data limited. Also, these two algorithms has a good performance in the application, but because there are many third-party cryptanalysis on SCON, so finally, the SCON would be selected as a standard. So, as this is the motivation, I want to do some of the cryptanalysis on the Sparkles family. So I think that what we can do that. Firstly, we are be good at to finding the distinctors, especially for the differential linear distinctors are very effective. For example, for the SCON computation, we can find the 3 or 4 round of practical differential distinctors. And due to recent years, we developed some the differential linear analysis on the X ciphers. We can find for the R side, we can find the 4 round deterministic differential linear distinctors. And we can to extend the RZ differential linear distinctor to the Sparkle computations differential linear distinctors. So we have so many effective differential linear distinctors. So can we use this highly based differential linear distinctor to speed up the image of the key recovery attacks? So next, another interesting thing is that the complementary portrait of the death. Such portrait is that we also use some of the related distinctor, but we never to do the oracle query with the really key. So such 3 interesting things. We want to do some of the per image or key recovery attacks. So the next is I will introduce briefly introduce some of the preliminaries to save time. I never give too many details. The first one is that the X translator. It means that if we give the set A, we will give all of the elements of the set A X shift to get the new set. The second, it means that if we get the linear subspace of then we can we can construct the partition for the wall input space. This is that if we get the linear subspace, we can do a partition of the wall input space. But this is some detail I will omit it. This is the introduce of the differential linear distinctors. So if we have this, I will to introduce that how to speeding up the per image attack. Let me to see some of the simple case. Suppose that we have the deterministic differential linear distinctor like this. That give F, we have the deterministic differential linear distinctor that is we have the lambda dot fxo plus lambda dot fxo plus delta is always hold equal to 0. If we have such a differential linear distinctor, we can check 2 guess per image with only 1.5 evolutions of F. We can do this. Firstly, we can guess the X, and then we compute the fx is set the corresponding tag. If the Y is equal to the tag, then we are done. We find the per image. Else, we can to text whether the lambda dot O plus Y is equal to 0. If the lambda dot O plus Y is not equal to 0, this means that the X plus data cannot be the per image. If the X O plus data is the per image, then this approximation must be held. So if we get the wrong guess, this approximation holds with the property about the 0.5. So on average, we do the 1.5 evolution of F. We can to check two per image. Of course, this is only one differential linear approximation. If we get many input difference, and for each difference, we can get many differential linear distinctures. Can we to get the better speed up? Then we do this. And we do this is that for each, firstly we set some numbers of we try such process. Then we can do this is that we can do for each input difference, we created some statistical test to check all of the differential linear distinct approximations corresponding to some one input difference. If all of the differential linear distinctures makes this corresponding the input difference pass the statistical test, then we to check whether the XO plus data is a per image. By this, we can do some we will do some we can to get the time complexity about our method. Is that this way we adopt some statistical test, which means that we must mix for the input difference, we mix the corresponding differential linear approximations is always equal to the value that's with high probability. That means that if the base is negative, we make the differential linear approximation equal to 1. If the correlation is not negative, is positive, we make the differential linear approximation equal to 0 as evaluated. So for this, because that each differential linear approximation for the wrong guess hold with property is about the 0.5. So finally, we can get such the time complexity. So if we have this is our method to speed up the per image tag. But this search is that the input space we can only find one that equal to the tag is okay. But for this is the susceptibility of our method. This set the lower bound, if we try the n times, then the susceptibility is lower bound by this. And the root and the tau is dependent with the number of the input difference we used. The rho is dependent on the correlation of the differential linear approximation and the number of the input difference we used. So we always set the n equal to the rho dot tau and inverse to make the successful probability is about the 0.63. Why we set this is that for a hash function, if we try the group power for the hash function gives the output the text with n bits, we always if we try the 2 power of n times, then we can get the correct per image. The probability is about the 0.63. This is always to do computation about the trivial attacks. So next is that how to spinning up the key recovery attacks. Because that we have the idea to spinning up the per image attacks, is that we only to get the input space and to search for the per image that this calculation is equal to the tag. But for the key recurring attacks, we need to through all the walls input space so to get the correct keys. So in order to this, the idea is very similar like the per image attacks, but the one difference is that we can use the related key differential linear distinguishers to do this. And by this, sometimes we must mention that we must mix the input difference for the key space become the linear space, because this can be make sure that we can go through all the views of the key space in order we can get the correct key. So this is the difference from the splitting up with the per image attack between the key recurring attacks. The process is like similar like the previous method. So this is the final the complexity is very similar. So use this, and with some things we must mention that if we have too many differential linear distinguishers, the complexity of the testing process is not negligible. This means that if we have many differential linear distinguishers, the test time may be greater than the evolution of the F. So in order to avoid this problem, we use some of the hash table to solve this problem. But this makes me that we need some additional memory resource to solve this problem, to use the memory to save the time of the caused by the testing process. So this is I do some example about how to solve this problem. First, suppose that we have such a function that is, I think this is the key piece, and this is the plan test to mapping 256 cipher test. And for this, we have some deterministic differential linear distinction, such as we have for the lambda I, the lambda 0 to the lambda 100 and the 37. Do this, we can get the 128 differential linear distinguisher for every input difference. The number of input difference is about the 2 power of 128, like this. So for each input difference, we have the same output masks. So if we have this, how to solve the problem how to save the time of the testing process? We can do this. First, we can do like the similar. Then we use the error that with the consistent with the output mask. We get the C data I. We can do some calculation about this, makes the stress and insert the data I according to this stress. Then by this, if we do a test, this is similar. But if we do test the data, whether the data I need to be checked, we can check whether the data is in the address whether it is in the address. If it exists, we need to test the data. If it's not, we may be omitted and do another. So from this, we only need the time to do the key recurring attack. But this the time complexity is about the 2 power of 128. So this is how to solving the problem is that when the differential linear distinction is too many, we will use the hash table to solve such problem. By this, we can do some. I will introduce some applications. First is that I do the applications of how to do the per image attack on the XOH. The SOH is a sparkle. The sparkle family is a lightweight hash function, but is that some difference is that when they absorbed into the read, they must to be the message connected with 138 zeros to do some linear operations to absorb. So how to do some of the attacks? We can do. This is the permutations of the sparkle. This is some of the nonlinear operation of the sparkle. This. So we can use some of the differential linear distinguisher for the RZ box. So we can do find such highly based differential linear approximations of the RZ box. By this, we can to extend the RZ box to the 1.5 steps sparkles computations differential linear distinguisher. By this, we can do spinning up get the spinning up factor about 2 power of 4.336. By this, we can do the spark. So we can do the we can do this. We can do the per image types for the 1.5 steps the SOH, and we do the 2.5 steps XOH family. There are some big difference because that this we need to some additional techniques such as per computation to do this attacks. We will need the spinning up factor about the 2 power of 2.24 to do the attack of the H to the H, and other variant of the H is also seen. Then we can do. I will reduce how to do the parameter attacks on the XCON family's lightweight hash. For because that we mentioned something is that this is construction of the XCON. Because that the XCON have some property is that the rotational inverse means that if we input this input difference and the output mass is if we attack is this, so we get some correlation about such differential linear approximations. If we upon this, if we active the input difference like in this, and same corresponding makes the input output mask active as this, then this differential linear approximations correlation is same as the previous, because that this so-called XCON's rotational invariance. Use this, we can do, if we find for the one input difference, we find many output marks makes the differential linear approximation have high correlation. Then we can do, by this, we can do get many differential linear approximations. So use this property. So we first for the 3-round SOF, 3-round SO commutation, we can got some such determinative differential linear distinction. By this, we can do the parameter type for the XOF. First that we can to use the 4-5 message, and we mix the input difference called that the M4, and then for the output mask we select this. This causes some of the differential linear distinction. Then by our algorithms, we can do the speed up factor. It's about the 2 power of 8. Like this, we can do the 4 rounds SOF by some differential linear distinction with high correlation. Then we can get the spin up factor is about 2 power of 2.53. Like this, but how to do the SCON hash, how to do some of the per image attack. But for the in the recent research, like in the crypto 2022, someone point out that the security of the SCON is about 2 power of 192 instead of the to power of 138, because that based on this new research, we do the image test on the S1 hash in this security climate. Then how can to do it? Firstly, for the trivial attack, for the sponge attack, we always take this to fix the rate part of the rate is equal to the T0. For then we search the part of the capacity to make is that in the next generation, they can to generate T1, T2, and T3. So this is the first phase that we need to search some the state of the capacity. Then after we search for the such state, then we do the background computation, and then from this we do the foreground computation to get the clearance at the part of the capacity. So we can do the such two phase to do the image detect for the sponge-based hash function. But the problem is that
try to wrap it up. You're already over time.
Okay, I'm trying. Okay, so we can do that is that we can to use our method is that to speed up this such the state find. From this, we can to get the speeding up factor is about 2 power of 8. That is the complexity of the S1 hash. Then we can do the four round S1 hash attack, like get the speeding up factor about 2 power of 3.38. Then finally we can do the key recovery attack of the 3.5 steps of the Schramm, and then we can to extend this attack by the 1 steps. Then finally we can go the 4.5 steps Schramm attack. In summary, we can get this the analytic result of some of the hash function. And then for the Schramm, we firstly gave all of the version of the Schramm. We gave the first wild key recovery attack. Compared with the designer document, our attack is not beyond the data limited. Finally, for the block cipher CXS we gave the 4 round key recovery attack. Also is only slightly better than the trivial attack. So this is our analysis result of our method. Thanks.
Thank you. So unfortunately, we don't have time for questions, so we will move to the next talk.
Pointer. Those are the forward and backward. You take that off. Just take that off so we can get it.
Yeah, thank you.
So we now have a third talk on the differential linear cryptanalysis. The title is New Approaches for Estimating the Bias of Differential Linear Distinguishers. The paper is by Tim Peng, Wentao Zhang, Jingxu Wang, and Tianyu Ding. I'm sorry if I'm mispronouncing it again. And Ting will give the talk.
Yeah. Good morning, everyone. My name is Tim Peng, and my talk is about new approaches for estimating the bias of differential linear distinguishers. I will introduce my work from 4 parts. And the first is the background and the previous work. As we all know, the differential and the linear cryptanalysis are the two best-known cryptanalysis techniques for symmetric key primitives. They have been used to analyze numerous ciphers. Based on these two techniques, a combination called differential linear cryptanalysis is introduced in 1994 that by the Nanford and Herman. That is, a cipher can be decomposed as a cascade E0 and E1. Then, and E0 is a high probability differential, and E1 is a high bias linear approximation. When the probability of the differential part is P and the bias of linear approximation is Q, the overall of the differential linear distinguishers will be 2pq squared. In order to estimate more accurately bias in Europe Crypton 2019, there is a new concept introduced which called DLCT, that then an attacked cipher is divided to 3 subciphers. That is the differential part and the middle part and the linear part. Assuming that the bias of the linear part is R, and then the theoretical bias of a differential linear approximation will be 4pRq squared. With the DLCT, the authors further improved the differential attacks on S4, Serpent, Ascon, and DES. In our paper, we establish a link between the bias of a differential linear distinguisher and the probabilities of a series of truncated differentials. First, we consider the differential linear probability, which can be which can be used to compute the bias of a differential linear distinguisher, and we call it DLP for short. In the differential linear bias is DLP minus 1/2. And then we will show how to convert DLP to the sum of multiply truncated differential probabilities. For Formula 1, we can see that the estimate of DLP can be converted into probability of calculation of EDT. That is, we need to judge the lambda delta I is when satisfy this equation. However, if we write the inner product lambda and the delta I using their bits, then we have another crucial observation, that is, if the lambda j equals 0 always holds, then this equation always holds. That means the value of this the bit of delta I does not affect the value of this equation. And therefore, we only need to consider the value of delta ij, that the lambda j equals 1. by definition of a truncated differential, the set of 2 to the power n delta I can be divided into multiple subsets. Each subset correspond a truncated differential. Therefore, there is a relationship between DLP and the truncated differential. To efficiently compute the probability of a truncated differential, we introduced a new concept, the truncated differential distribution table. We call it TDT. This is a three-dimensional table, and for the determined input difference, this table can help us compute the truncated differential probability of a S-box. There are two propositions of the TDT, and the first is the TDT is an extension of the DDT, and we can get the entry of TDT with the DDT. And the second is that we can compute the DLP using the TDT according to the relationship between the DLP and the truncated differential probabilities. On the other hand, we have 4 properties of the TDT, which can be observed from its definition easily. Okay. Now, we show how to estimate the DLP based on TDT in practical. Since in our paper, we assume that the cipher is a Markov cipher. That means the probability of truncated differential characteristics often computed by multiplying the probabilities round by round. Then we can get the formula 2 and the formula 3. Since in our paper, the input difference of TDT is a determined difference. So we limit that every Tij A is either a determined difference or a truncated difference, but all output difference bits are arbitrary. Finally, there is a relationship between DLP and the TDT, and we can compute DLP at the level of the Xbox, and we can compute the DLP round by round. Since the TDT is a three-dimensional table, and we want to know if we can get get some useful information by making some pre-computations. So we introduced a new concept of differential linear pattern, and this is assist in making sure whether a Xbox in the output difference of S layer is ignorable or not. And this is an example. And the figure 1 is the forward propagation of delta, and the blank cell indicates the bit difference is active and inactive, and the blue cell indicates the bit difference is near to be determined, and the figure B is the the propagation of delta, and the yellow cell indicates as the beta difference near to be determined, and the red cell indicates the beta difference is arbitrary. We combine these two propagations and get the differential linear pattern for every beta difference, and there are 3 cases. And the first is a beta difference is inactive in the forward propagation. That means it will always be inactive, and we can ignore it. And the second is that the beta difference is arbitrary in the backward propagation, and there is no need to consider its value. For these 2 cases, we set the differential linear pattern as 0, and for the other case, and we set this means that we need to determine in the beta difference, and we set its differential linear pattern as 1. For each X box, the case of the differential linear pattern equals 0. It means we can skip the S box, and we only need to consider the case that differential linear part is non-zero. After that, we can compute the differential linear pairs, and there in our paper there are 2 methods to compute the differential linear pairs, and this is the first that is the case that the middle part consists of multiple rounds, and we complete this work in 3 phases. The first one is computing the differential linear pairs of EM using the breadth-first method, and the phase 2 is extending a differential in the differential part, and a linear approximation in the linear part. The order of phase 1 and phase 2 is not fixed, and can be adjusted according to our needs. And finally, compute the overall base of the differential linear base errors. When computing the differential linear base of the middle part, we offer a round-by-round approach to compute the truncated differential probabilities. And in the last step, we need to check each candidate of BRN -1 and judge it if it satisfies this equation, accumulated its probability to DRP. In each round, we need to traverse table AI -1 and the AI, and so we can get the computational complexity. And for the memory complexity, in each round we must keep 4 tables in these 4 tables. 2 for two for current round and the two from previous round. Sometimes this method can compute the base of differential nonlinear base correctly, but sometimes it is difficult to compute the base of middle part. So we try to use, so we have another method, and we try to use the LCT to connect a truncated differential and a linear approximation. In this case, the question is how to compute the probability of the truncated differential in the phase one. In our paper, instead of conducting an exhaustive search, we evaluate the truncated differential probability by finding as many as high probability truncated differential characteristics as many possible using TDT. And our program is based on depth first search with the branch and bound technique. We set a threshold in the traverse of possible truncated differential characteristics whose probabilities is greater than the threshold. And then this is the method to compute the probability of a truncated differential. In our paper, we apply the two approaches to 5 ciphers. They are Asken, Cannot, Serpent, AS, and Clefairy. For Asken, we revisit the 4 and 5 round differential nonlinear distinguisher, and for the fourth round differential nonlinear distinguishers, we get a base as in accordance with the experimental results. And for the 5 round, our base is extremely close to the experimental results. And we also construct a 6 round differential nonlinear distinguisher. For Serpent, we revisit the 4 and 5 round differential nonlinear distinguisher and the results. And the results are both close to the experimental results. And apart from this, we search for the differential distinguisher up to 9 rounds. Especially for the 9 rounds. If we ignore the key recovery attack, we can get a better base, and this is 2 to the minus 52. But if we take key recovery attack into consideration, we can get two better differential nonlinear distinguishers, which the pairs are both these. And this is the result of Cannot. and we search. In this case, we consider the properties of initialization phase. So we can control key recovery in attacks in the future. We get different differential linear distinguishers for not up to 60 rounds in the 60 round differential linear distinguisher has a base of 2 to the minus 30.52. AS in the classifier are the batch white ciphers, and we apply our methods to them. For AS, we search differential. We search up to 5 round, and the 5 round the differential linear distinguisher has the base of 2 to the minus 51.85 in the classifier. We search for up to 9 rounds. And this is the result. Okay, that's all. Thank you. Any questions?
Thank you. Unfortunately, we're a bit late, so I don't think we'll have time for questions. So we will move to the final talk. So the
We had to switch the audio to the other computer to play the video back. Sorry.
Okay, so the last talk is probabilistic linearization, internal differential collisions in up to 6 rounds of SHA-3, and it will be a pre-recorded video by Zhongyi Zhang.
Okay, thanks very much for the introduction. Good morning, everyone. I'm Zhongyi Zhang from Institute of Information Engineering, Chinese Academy of Sciences. It's a great pleasure to present our work today. My topic is the probabilistic linearization internal differential collisions in up to 6 rounds of SHA-3. This work is done together with Chen-An Ho and my PhD supervisor, Mei-Qing Liu. My talk will be divided into these aspects. Let's start with a short description of the background of Kichak and also the previous work and our contribution. This is a short introduction to Kichak, which is one of the most important algorithms in hash function. After MD5 and SHA-1 were threatened, NIST opened the SHA-3 competition in 2007. Kichak was submitted to the competition in 2008. Its designers are Bertoni, Diamond, Peters, and Asha, and 4 years later, Kichak became the winner. In 2015, it was standardized by NIST as SHA-3. SHA-3 has 6 versions, including SHA-3 224, 256, 384, and 512, and 2 extendable output functions. The difference between them lies in the length of the output digest. Now, let's take a look at the previous work and our contributions. We utilize the internal differential cryptanalysis, which is developed by Thomas Perrin in Crypto 2010 and generalized by Diener, Dinkelman, and Shamir in the analysis of Kichak. In the FSE 2013, Diener et al. Mainly used the following 2 techniques: generalized internal differential and targeted internal difference algorithm. They proposed practical attacks on 3-round Kichak 384 and Kichak 512, and theoretical attacks on 5-round Kichak 256 and 4-round Kichak 384, all of which were the best results at the time. Afterwards, at the Eurocrypt 2023, we proposed conditional internal differential analysis and improved targeted internal difference algorithm, which resulted in theoretical collision attacks on the run reduced of 6 versions of SHA-3. This table summarizes the results of collision attacks on run reduced SHA-3. The final row shows our analysis. The major contribution of our work is that we utilized the internal differential attack to propose the collision attacks on up to 6 rounds of SHA-3 versions, where we introduced the first ever collision attacks on 5-round SHA-3 384 and 6-round SHIC 256 in the latest results. Part 2, an overview of the attack. Okay, next we will briefly introduce internal differential cryptanalysis. In standard differential cryptanalysis, we consider messages pairs which make up a pair of states and consider the evolution of the difference between the states. However, in internal differential cryptanalysis, we have only a single message and we divided it into 2 parts. And we are tracking the difference between the parts of a single state. For generalized internal differential cryptanalysis, we consider more complex differential relations between multiple parts of a single state and their evolution. For conditional internal differential cryptanalysis, we can find the messages confirming 2-round internal differential characteristic by adding linear conditions to the initial state space. In our latest work, we introduce a new targeted internal differential algorithm using a probabilistic linearization method. Simply put, by adding linear conditions to the initial internal differential space, we can find the first message block that satisfies the targeted internal differential characteristics with a certain probability. Let me briefly introduce the internal state of SHA-3. Kichak F has an internal state of 1600 bits, which can be seen as 5 × 5 matrix, where each cell is a 64-bit line in the direction of the axis. Its round function R consists of 5 steps: theta, rho, pi, chi, and alpha. The linear layer is the first 3 steps. Chi is the only nonlinear operation. Alpha can't be ignored in internal differential cryptanalysis. The figure on the right is some notions defined by the designers. Now let's look at a special type of states which we would call symmetric states. One state has period I in the z-axis, such as shown by the following formula. It is called a symmetric state and since the fundamental period corresponding to I is the greatest common divisor of I and 64, I can attain non-trivial values 1, 2, 4, 8, 16, 32. Here is an example of a symmetric state with period I equal 16. For internal difference, we will introduce the concept of internal difference sets. Given a period I, the set by adding a single representative state V to all symmetric states is an internal difference set, which is called internal difference for short, recorded as IV. If V is the zero vector, IV is a zero internal difference, and exactly the set of all symmetric states with period I. Finally, similar to the case in quotient groups, the action of linear mapping on any internal difference is equivalent to acting on the representative state, just like the following formula. Now let's look at the framework of the attack. For 5-round collision attack, we choose 2 block messages as inputs and employed the target internal difference exam to complete the first step. Next, we applied conditional internal differential techniques in the initial message space to select an initial message M1 that can pass through the first 2 rounds. This ensures that M1 enters the second round's internal difference set under the given internal differential characteristics. Next, calculate the internal difference of message M1 after 4 rounds of round function and store the states into the subsets. Finally, calculate the collision subset in turn until one collision is found in a certain collision subset. The complexity of the attack consists of 3 main components. The total time complexity is determined by the greater of complexity of the TIDA stage and the complexity of the remaining parts. Alright, next we will introduce the basic techniques for the following 3 questions. How to improve the target internal differential exam using the probabilistic linearization, how to contrast internal differential characteristics, and how to calculate the expected size of the collision subset to more currently estimate the attack boundary. This is the third part. Let's begin with the first question. The purpose of designing the target differential exam is to contrast connectors and solve connectivity problems. In a collision attack on SHA-3 with NR rounds, an N1 round connector output message M0, M1 that satisfies 3 conditions. The capacity and padding parts of initial messages, values, and the input difference must be fixed, as this cannot be controlled by the second message block M1. The third point is that the output difference after N1 rounds should match the target difference, thereby connecting the message with the differential characteristic. In the internal differentials, this problem can be expressed as an internal connectivity problem, which corresponds to a 1-round internal connector. To describe and solve this problem more conveniently, we introduce the following 2 definitions: the input difference system and the inner part of the input difference system. Simply put, if the entire state of the input difference is considered as a variable vector, the linear system related to the input difference is called the input difference system, denoted as E big delta. If Gaussian elimination is applied to E delta, the equations that contain only the variables corresponding to the capacity and the padding parts, that is to say that the last C and P variables are referred to as the inner part of the input difference system. The value in this part cannot be controlled by the second message block M1 and depend slowly on M0. After introducing the two definitions, let's see a property of the S-box. The S-box has 5 bits inputs and outputs, meaning that 5 bits variable from a 5-dimensional linear space. A t-dimensional affine subspace within this 5-dimensional space can be equivalently represented by the solution space of a system of linear equations, as shown in the top equation. Next, we introduce the concept of difference destiny. Given an output difference dealt out of the S-box and an affine subspace U, the number of input differences contained within U is called the difference destiny. For example, if the output difference is 0x05, we can identify a 4-dimensional subspace. The subspace with the highest difference destiny is referred to as the maximum difference destiny subspace. In this case, 0x05 has 10 input differences, 7 of which are contained in the subspace kernel 0x011. When solving the input difference system, the solutions may not always be valid input differences. When solving the input difference system, the solutions may not always be valid input differences. The probability of correctness is 7/16. However, this method significantly reduces the number of equations required to contrast the input difference system. Let's take a look at the results. Take the example of 5-round Chasserie 384. In the first round nonlinear layer, there are 160 S-boxes with 77 active S-boxes and 83 non-active S-boxes. Each non-active S-box has 5 equations and each active S-box has 3, resulting in 646 equations in the input difference system, with 234 equations in the inner part. Note that this inner part cannot be controlled by the second message block and must be satisfied by randomly selecting the first message block. The complexity of selecting the first message block is 2 to the 234, which far exceeds the birthday bound of 192. Using the probabilistic linearization, where only one equation is added, the system now has 492 equations with 96 in the inner part. However, the solutions to this system are not necessarily input differences. The probability of obtaining a valid input difference is 2 to the power of negative 64.61. This means that on average, 2 to the power of 64.61 attempts are required to obtain a valid input difference. The cost of finding a solvable system is 2 to the 97, leading to a total complexity of 2 to the 161.61. The second technique involves contrasting internal differential characteristics, which we model and solve using MLP. A good characteristic needs to satisfy two conditions. First, the differential transition probability in the first round should not be too low. If it is, too many degrees of freedom will be consumed, leaving inefficient messages to enter the correlation subset. Second, the inner part of the input difference system should not contain too many equations. As we saw earlier, this directly impacts the time complexity of TIDA stage. However, these two conditions are inherently contradictory. To strike a balance between these two guidelines, our internal differential characteristic shows that the number of active S-boxes is about half of the total. Here, key I refers to the differential transition probability in the ith round. Finally, let's briefly introduce our approach to estimating the size of collision subset. Taking an example where the output digest length is 64 bits, which corresponds to the first line of the state. This line is controlled by the first 3 lines of the input to the nonlinear layer. In previous work, we estimated the size of the collision subset directly by considering the size of these first 3 lines with I equal 32. A collision in the first 3 lines before the nonlinear layer would lead to a collision in the first line after the chi operation, but this is only a sufficient condition. In our new work, we adopt a strategy that estimates the size of the collision subset by calculating the expected number of messages needed to produce a collision. This method allows us to obtain a more current attack boundary, as shown in the table below. The table shows the expected size of the collision subset when the line length is 64 bits, with the output length being less than or equal to 10 lines. The last part is the results and the summary. First, we present a small-scale example of a collision attack where the complexity and weight parameters match the Kick-Check challenge, but the output length is 96 bits. The parameters of internal differential characteristic are shown on the right. The theoretical complexity is 2 to the 42.5, and the actual complexity is 2 to the 43. The table lists the attack results on 6 instances of such 3, along with parameters of the internal differential characteristics. This is summary and future work. For this work, we proposed the first collision attacks on 5 round SHA-384 and 6 round SHIC 256, and our results for 4 round SHA-3 512 have set a new record. An interesting future work is to find better internal differential characteristics for Kick-Check. Maybe we can apply internal differential analysis to the other ciphers. That concludes my presentation. Thank you for your attention.
So we don't have time for a question, but if you have questions, please send them by email to Zhongyi. And this is now time for the break. So let's thank the speaker again and enjoy the break.